Hello, in this video I'm going to talk about neutral attraction, which is this fascinating phenomenon where a neutral object actually will be attracted to a charged object. Or you can think of it as, I guess, a charged object being attracted to a neutral object, because Newton's third law, force of A on B equal and opposite to force of B on A. So you may have done this experiment before. If you take a balloon and rub it on your head, you can usually, if this is going to work, you can, it's a little unhappy, but you can make it stick to the wall. So I can make a balloon stick to a surface, even though the surface, this glass that it's sticking to, for you, it probably looks like it's in midair. Okay, well, there's glass here. That's what I write on. Okay, so the balloon is sticking to the glass. I charged the balloon by rubbing it on my hair, but the glass is neutral. There's no extra charges on the glass. So how does this work? What is this idea of neutral attraction? Neutral attraction. And to explain this, I am going to use a model. Now, this isn't actually what exactly happens in the materials, but it is a very useful way to model what is happening. So if I have a balloon and it's sticking to a wall, a glass, whatever. All right. Let's think about what's going on. When I charged it by rubbing it against my hair, charging by friction or charging by rubbing, what that does, one object becomes positively charged, one object becomes negatively charged. And you can see my hair, yep, it just made a shocking noise. So my hair became charged, the balloon became charged. Based on something called the triboelectric series, and you can look it up, you can see that things like hair and wool tend to become positive. They like giving up their electrons. Plastics tend to grab electrons. They're greedy for electrons. So my hair became positive because it gave up electrons to the balloon. The balloon now has extra electrons on it. So that's a start. I'm going to say that I put a couple extra electrons onto the balloon. And now here I'm going to shift to the model instead of the physical, actual what's happening. I'm going to talk about it in terms of there's just extra negative charge. So I'm going to talk about positive charges and negative charges. This is my model. Okay, I have extra negative charge on this part of the balloon. Because the balloon's an insulator, charges don't move easily. All that charge, even though these negatives are repelling each other and trying to get away, because they can't move easily on an insulator, they're just stuck there. So they're stuck there. If I try to get the balloon to stick in a different place, yeah, there's nothing happening there. So maybe it'll still stick. I don't think about it. Okay, now what is stuff made of? So stuff is made up of atoms. Atoms have positives, negatives. They've got the protons, the neutrons, the electrons. But I'm just going to talk about atoms as being made up of positives and negatives. Again, this is a model. So if I think about the atoms, not to scale, that are hanging out in the wall or the glass here, what are the charges in the atoms doing? Well, the positive part of the atom is going to be attracted to those negatives. So opposites attract, so the positives are going to say, I like being over there. The negatives are being repelled by these negatives. Likes repel, and so the negatives are going to go away. All right. So how does this help explain? Well, you got to think about what factors affect this repulsive force, attractive force, or the repulsive force. You can imagine that more charge means more force. So you put more charge on the balloon, there'll be a stronger attraction to the glass. The other piece of the force, the electrical force between two objects, the other piece of it is distance. So if I charge this up again and I put it here, no, it's not attracted. I have to get it real close. I think I took away all the charge. Yep. I have to get it pretty close in order for it to stick. So distance is one of the pieces for the force between charged objects. And bye-bye. So you can imagine that farther apart, less force. Closer together, more force. So what happens with neutral attraction? The positives are pulling the balloon towards the glass or the wall because opposites attract. The negatives are repelling the balloon, so they're pushing the balloon away. So why does it overall attract? Well, it's the distance piece. Because these negatives are farther away effectively than the positives, we have a larger positive attractive force and a smaller repelling force. I just made a mess. So we've got this smaller repelling force and a larger attracting force. What's going to happen overall? Attraction. And so neutral attraction, there's two pieces really. There's this moving around of the charge, and we call this polarization of charge. Polarization of charge. And that's where, in our model, the atoms are reorienting themselves to be plus minus, like this. So that's the first part of neutral attraction. The second part is the distance. So because of the likes are always going to be farther, the like charges are farther away. Like charges are farther away. Oop. Hello, balloon. That means the repel is smaller. So that's the second piece of neutral attraction. First, the atoms, they polarize, so we've got the pluses on one side, negatives on another side, and then because the negatives are farther away, we have a strong attraction, weak repulsion. Overall, it's an attraction. So that is neutral attraction. So don't just stop here. If you're explaining neutral attraction, don't just stop with polarization, because, right there doesn't explain anything. I still have an attraction and a repulsion. You got to explain the other piece, which is that distance piece, giving us a larger attraction and a smaller repulsion. So there you go. Hope this was helpful.